All right, welcome back to calculus. Today we're going to be looking at more limits to infinity. We'll look at limits to positive infinity and negative infinity, but the difference for today is that the types of functions that you're taking limits of are a little more complicated. So we're going to add to what we know about finding those limits. Now, we're going to work some of the examples on page 24 in your notes packet, but unfortunately there's not a lot of good examples in your notes packet, so you'll probably want to add an extra piece of paper. That's why I gave you your note packet with holes punched in it, because I was hoping you guys would grab a binder and put those notes in the binder, so that would make it easy for you to add or subtract papers if you need to. So let's build on that reasoning from the last lesson where you were trying to identify the limits as x approaches infinity of functions that looked like this. So the first one, the limit as x approaches infinity of 5 over x squared, you would get that limit to equal 0 because the degree in the denominator is higher. The middle one, you would end up getting the limit as x approaches infinity of x squared plus 2 over x. You would get this limit to evaluate to be 1 because the degree of the numerator is the same as the degree of the denominator. So you would look at the ratio of those leading coefficients, and 1 divided by 1 is 1. Now, in the third example, where the degree in the numerator was higher than the degree of the denominator, you would have to say, okay, well, to evaluate this limit, I know it's going to either be positive infinity or negative infinity, and we just have to check for the sign. Okay, well, today we are going to keep the same reasoning, but like I said before, our functions are going to get a little more complicated, and we need to add the idea of dominance. So, what is dominance, or what do I mean when I talk about dominance? When I talk about dominance, what I'm thinking about is I want to know which types of functions grow faster than the others, or which types of functions grow the fastest. And so you're going to be given functions that have terms. Some of the terms are log terms. Logs are natural log terms. So remember that the abbreviation for natural log is ln. Logs are natural logs. Then you'll have polynomials. Oh, I can't spell polynomials. And you'll also have exponential functions. And so we need to figure out which of these types of function grows the fastest. And just as a reminder, logs are natural log functions. You'll know if it's a log or natural log term if you see something like the log of x or natural log of x. You'll know, and then you'll know if what you're looking at is a polynomial if you see an x raised to a power like x to the 12th or x squared, or maybe even x to the 38th. Those are polynomial terms because the base is an x and the exponent is a constant or a number. The exponential terms are the terms that have an x as the exponent. So you might see e to the x or maybe 3 to the x. And so we are going to compare these three functions and see which type grows the fastest, because that's really going to help us figure out our limits today. So I have on Desmos, I have three functions graphed, and right now it looks overwhelming. So let me unhighlight. So right now, the function that's graphed is x to the 12th, the red function right here. So that's a polynomial function. And I have this slider a. So right now it's on a equals, let's see, a equals negative 10. So that means if I want to evaluate the function f of x equals x squared, then I would substitute in negative 10 for the x. And this line right here shows me what I get. So like if I were to say, what is f of 300? I can just look at this line and say it's 5.31. 0.1441 times 10 to the 29th. So the red function, that is our polynomial function. Take that one off. The blue function is the exponential function. So exponential functions all generally have this shape. It looks like it's growing pretty fast. I can see that if x was 300, g of 300 would be about 1.94 times 10 to the 130th. So that would be pretty large. And then our last type of function is a log function. That function is going to be graphed in green. And if the a value or the x value was 300, like what I'm showing up here, then that value of the function would be 2.477. So if we look at all three functions graphed at the same time, then I see this picture and it looks like the green log function is growing really slowly. So far we can tell the log function grows the slowest. Then I have the red function that takes off and follows this motion. And so it grows quickly, and actually it kind of looks like it's growing faster, like it's getting, the y values are getting higher faster than they are in the exponential. But if I increase the x value to maybe like, I don't know, 725, well, that's going to go off 660. Then I'll notice my polynomial function, that y value is something times 10 to the 33rd, but the exponential function is much higher because it's 4.3 times 10 to the 286. So it looks like the most dominant function, the function that's growing larger the fastest, is the exponential function. And then the polynomial function after that, and then the log function. Okay, so all of that is to say, when we're thinking about dominant functions and dominant terms, one thing you need to remember is that the log, I need a pen. One thing that you need to remember is that our log functions grow the slowest. So log or natural log, those functions grow the slowest. And then the polynomial functions are a little bit more dominant than the log functions. But then the exponential functions are the functions that are, we call the most dominant, meaning that they grow the fastest. Okay, so why do you need to know about this? Because whenever you're working the problems we're going to do today, one skill you're going to need is you're going to need to be able to identify the most dominant term. So you'll identify the most dominant term, and then you're going to need to apply some critical thinking skills. So we're going to have three scenarios here. Okay, the first scenario is where you have the limit as x approaches infinity of something over something else that's growing really fast. So to make this a little more concrete, if you were to think about the number 5 being the something part, and a really big thing, maybe like 100,000. Well, 5 divided by 100,000 is 0.00005. So that's pretty much 0. And if I were to increase 100,000 to 1,000,000, I would get a value that's even closer to 0. So if you have the limit as x approaches infinity of something over something really big, you're going to get 0. So you'll probably want to write this down. If the denominator is growing faster then the limit as x approaches either positive or negative infinity of a function is going to be 0, which is really nice because it's super straightforward. The second case is where we have something that's really big over something else that's really big. So if I were to think of a really big number, let's say like 100,000 divided by a really big number, but maybe slightly different, like 100,003. That's approximately 0.99999, which is pretty much 1. So what that means is that this extra 3 right there, that's not making that much of a difference when you have to divide, especially when those numbers get really, really large or really, really small in the negative direction. So the case that we have here, the second case, deals with if the denominator and the numerator are growing at the same rate, then you're going to look at the ratio of the most dominant terms. And that's really similar to what you guys did last class, where you had to look at the ratio when the degrees in the numerator and the denominator were the same, and you looked at the ratio of those leading coefficients. The last idea is if you have something, the limit as x approaches infinity of something that's really big over something else. So concretely, that would be like if I had about 1 million, I need a different color. There we go. Like if I had 1 million divided by 5, that's going to give me a large number. Now, if it were a negative 1 million divided by 5, it would be a very small negative number, like negative 20,000. So this is a case where you see if the numerator is growing faster, then your limit as x approaches either infinity or negative infinity of f of x, so in either direction, that is going to be equal to either positive or negative infinity. So we're going to get an infinity as an answer. And you're going to have to figure out whether it's positive infinity or negative infinity. Now, I do need to make a special note. So special note right here. If you evaluate a limit and you get infinity, technically infinity is not a number. So technically, these limits do not exist. Because they don't actually approach, they approach a direction like towards positive infinity or towards negative infinity, but they're not actually approaching a solid number. So technically these limits, we would say, do not exist. But I feel like I feel like we can always specify more. And so I'm going to ask you to most of the time specify the direction, but we can specify the direction. And I say that because the first couple problems on your homework assignment has you to just determine whether or not the limit is going to be 0, if it's going to be something else, or if it's going to be it does not exist. And so then those you would answer does not exist. But in the sections after that, I do ask you to specify positive or negative infinity. And then if this were a quiz, I would always ask you, a quiz or a test, I would always prefer the positive and negative infinity part. So let's look at a couple examples from Delta Math. So here's one like Delta Math. You'll have a couple that are multiple choice, and you have to decide the statement that best describes the limit shown. So we have the limit as x approaches infinity of e to the x over the natural log of x plus x to the 37th. So what you're going to do on these is the first thing that you're going to do is you're going to identify the most dominant terms. So my most on the numerator and the denominator. So the most dominant term in the numerator is e to the x. The most dominant term in the denominator is the polynomial term x to the 37th. After that, after you identify, then you're going to compare. You're going to compare, and when I say compare, I mean compare like what I was talking about before, where we have these three different cases. So when I say compare, I mean refer to this chart right here. Is the denominator growing faster? Is the numerator growing faster? Or are they growing at the same rate? So going to compare. So I see, it looks like the thing that is growing faster is the e to the x. So it looks like here the numerator is growing faster. Which tells me that I'm going to be in the chart, the third category, what's written in the green of the chart. So my answer will either be positive or negative infinity. But I notice my options are not positive or negative infinity. So I'm going to take note of that special note right here that says, technically these limits, whoops, I need a highlighter. Technically, these limits don't exist, but we can specify directions. So when you have a question on Delta Math that doesn't ask you to specify the direction. So I'm in that third case. I know technically this limit does not exist. So I'm going to select this second one. Okay, so I know it can't be the limit doesn't equal 0. Boom, boom, boom. The third option, you would pick that third option, if the limit is a number. So if you evaluate the limit and you get like a solid number like 5 or 1 or -3, you would pick this option. But since we don't have this option, we know it's going to be a positive or negative infinity. I'm going to say the limit doesn't exist, and that's what I'm going to select there. The second example, here's another one. The limit as x approaches infinity of x to the 38th plus 10x to the 14th over x to the 38th. So the first thing I'm going to do, I'm going to look at my most dominant terms. So my most dominant term in the numerator is x to the 38th. Most dominant term in the denominator is also x to the 38th. Hey, look, those are growing at the same rate. So that is that second case where the numerator and denominator are growing at the same rate. So I'm going to look at the leading coefficients. I'm going to compare those, and I get 1. So I would select on this option that the limit exists and it does not equal 0. And then one more example like this. If I look at this next example, I'm looking for the most dominant terms here. So let's see, in the numerator, the most dominant term is x to the 21st. And the denominator, the most dominant term is 7x to the 28th. It looks like the denominator is growing faster. And when the denominator is growing faster, that's that first case from the chart above. So the limit equals 0. Okay, so this video will help you with the first section of problems.